divided by the rate of usage. Okay, and that's going to give us our estimate for the how long it'll take for this star to given its current mass to use it all up. So in this case, our fuel is, let's say, the total energy of this much gasoline. So we'd have something like 2 times 10 to the 30th kilograms times 5 times 10 to the 7 joules per kilogram over the rate of usage, which is 4 times 10 to the 26 joules per second. Now, just to get a sense for how big this is, 4 times 10 to the 26 joules per second is 4 times 10 to the 26 joules is pretty much more than the world's energy usage in a year, and the sun cranks through that every single second, which is pretty amazing. Okay, this translates roughly to about 2 or 3 times 10 to the 11 seconds. Or when you do the conversion, turns out to be about 8,000 years. Now, we know that this is wrong. And we know it's wrong simply because we've been around for longer than 8,000 years. We have archaeological evidence of humans being around longer than that, and we have, by a long time, we have fossil evidence of humans being around for about 100,000 years, and we have a lot of evidence that life has been around for billions of years. So this just doesn't work. So clearly, the sun is not powered by something as simple as gasoline, and that turns out to be correct. So what is the sun powered by, and can we use it to give us an estimate for how long the sun will be around? So we can do that, actually. So what happens is the sun is powered by its own mass being converted directly to energy. This is a consequence of Einstein's special theory of relativity, and we have the E equals mc squared. So all the E equals mc squared relationship means is that mass itself can, under certain circumstances, be converted to energy, and an awful lot of energy, because c here is the speed of light. 3 times 10 to the 8 squared is about 10 to the 17. So we're dealing with a very large amount. So if we want to look at the number of how long the sun will last in this case, then what we have is 2 times 10 to the 30th kilograms times the speed of light squared. So then we have 3 times 10 to the 8 meters per second squared. Alright. And this gives us somewhere around the order of 2 times 10 to the 47 joules. And even if we were using it up at this great rate, when you take this amount of fuel, divide by 4 times 10 to the 26 joules, you're going to get trillions of years. Now that too is actually an overestimate for how a star works. We need to have more detail on how a star actually works, but it does say that with using nuclear power, essentially by converting its mass directly into energy, the sun is able to fuel itself and still use up a lot of energy every single second and fuel itself for billions of years. And so a very careful analysis of it actually comes out to roughly around 10 billion years, which is then consistent with the biological evolution that life has been around for about 4 billion years. And we'll see other ways of measuring the ages of things like rocks, which we can show are billions of years as well. So the whole thing kind of hangs together and is consistent. So what are some of those details? Well, if we look at the elements, okay, and we have different types of the same element, which are called isotopes, which are differ from each other only in the number of neutrons. Any given atom or molecule or anything else is made up of a number of protons and a number of neutrons. Shown here is the number of protons. And so the mass of a given proton is this, out many decimal places. And if you take two deuteriums, so one proton, one neutron, and so we have one of those, and let's say we have two of them, so this is going to be about 4, and we combine them in a nuclear reaction, we can get helium, which also has a mass of about 4. But if you were to be careful and actually add these up, add this one times 2, compare it to this, you'll notice that the mass of the helium is somewhat less than the mass of the combined two deuteriums. Just a little bit less. And that little amount mass change is the energy that fuels the star. So the star, as it converts hydrogen into helium, loses a little bit of its mass, doesn't convert all of it, uses about 1%. And because of that, the star is actually fueled. Because it uses 1% only, that means that it's only going to live 1% of the lifetime that we naively calculated in the previous slide. So the star gets energy fusing hydrogen into helium. Shown here is actually a plot of the energy that you get